Hi, it's Mrs. Lemke. Welcome to our lesson on continuous growth models. So a continuous growth model by our labeling is any model that involves using the constant E. So understand that in this equation, the E that I just highlighted, that's a number, a specific number, right? That is the base of the natural log. And in this equation, as it is written, ordered pairs would be t comma y. I just as easily, and maybe just to be more general, I probably should have written it like this, which would mean my ordered pairs on the graph of this equation would be x comma y. So the things that are variables that vary are the x and the y, or a lot of times this is relative to time, so I like to use a t. In those cases, sometimes the t and the y. So variables are x and y or t and y. E is a specific number, and that means that the a and the k in all of these are what we would call constants. And E is a constant too, but it's a constant we already know. E is always going to be 2.718, blah, 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 okay? A and K are going to be different kinds of numbers in different problems, but within a given problem, they will stay the same. They will not vary. So variables vary, constants stay the same, okay? And so within a given problem, the value of A, the value of K will be something, right? It might be 7 or 1.3, right? So whatever it is in a problem is what A or K is. So sometimes you have to find out what those constants are. Sometimes they'll be given to you, depends, okay? So something that is a pet peeve of mine is that sometimes people really try to make a big fuss over like this equation or this equation, or even the changing of x and t here. These are all the same equation, you guys, okay? So it doesn't really matter what letters you use to represent the ordered pairs that are on the graph. You might use T with A, or T with capital P, or X with Y, or T with Y. It does not matter, okay? If you have variable equal sign constant times E to a different constant, I'll call it constant number 2, times your independent variable. Okay, these are not the same variable. Okay, it's the same thing. Okay, so do not get bogged down in what letters get used. Okay, just saying. Okay, so I now need to apologize because some of you have printed out copies of this packet, and right before making this lesson, I was looking through and I did make some edits. So I am very sorry for those of you who are now crossing things out to make it match what I am looking at. But these first 2 questions just needed a little work to really make the most sense, okay? So if you need to pause the video, if you're one of those folks, pause the video and do make the edits that you see in perhaps your printed copy versus mine. If you just printed the PDF for today that was posted, you're fine, okay? All right, so make sure your notes match and then let's go, okay? If your notes don't match, then I am answering a different question, and that would be bad notes. Okay, so it now says that the world population in the year 2000 was about 6.08 billion, and in 2003, it gives us another value. So really what we're being given here is a couple of ordered pairs. And if I glance ahead, I can see down here it says that X be the number of years past 2000. So since I'm going to have to do that in part B, I'm just going to start with that idea. And so instead of calling this year 2000, I'm going to call it year 0, right? Because it's the number of years past 2000. In 2000, I am not past 2000 at all. I'm exactly in 2000. So I have the ordered pair 0, 6.08. So this is time past 2000, so years past 2000, and this is my population in billions. Okay, so then that means that my other ordered pair would be 3, because this is now 3 years past the year 2000, and 6.35. Okay, so I'm being given two ordered pairs. And it says to write a function to model the world population. So assuming that there is some exponential growth here, assuming that model, I want to think about that equation that we were just talking about, okay? And it doesn't really matter what letters you use here, okay? But I'm going to go with this and say that this is some constant times x, okay? So my constants that I need to determine are the a and the k. E is a constant, but it's a known constant. X and Y are the things that vary, okay? And they vary, like they could be this pair, they could be this pair, it could be a lot of different points because there's going to be a lot of points on my graph, an infinite number of points. Now, the great thing about being given this first ordered pair is that if I put 0 in for x, okay, I'm just going to write this out to help you understand what I'm saying. If I put in 0 for x, this part leaves this blank for a second. This part is going to be e to the 0, and e to the 0 is 1. So this whole chunk doesn't matter because multiplying by 1, it's gone. And if I'd substituted in my other points, I would have, or the rest of that ordered pair, I'd have 6.08 equals my a. So whatever, the thing that goes in that slot is like your initial condition. And sometimes you're told that straight up, and that's a huge time saver, okay? So my work for this, like this part, I wouldn't have actually written because I already knew that. I would just say, okay, I have 6.08 as my initial condition, and then my eyes would go to this other ordered pair that says, all right, when I plug in 3 for x, I get 6.35 billion for y. Okay? So there's all my numbers substituted in. And now I just get to do the fun work of some algebra, okay? And so I would divide both sides by 6.08, okay? And let's go to the calculator and do that together, okay? So what was it again, 35? Divided by 6.08. Is going to give me that number on the left side of my equation. So that's 1.0444 blah, blah, blah. And I'm not going to worry a whole lot about what I write down there because I'm going to use that entire output in my next step. I do not round in the middle of a problem. Okay, but whatever I write on my paper is just representing my calculator work. Okay, now I'm taking the natural log of both sides. The reason I would take the natural log of both sides is so I can use this log property that lets me put that down in front. And so I would have just the natural log of this output from my calculator screen is equal to 3 times k times natural log of e. Oh, natural log of e is 1, so I don't need to worry about that. So on my calculator, I just need to do natural log of that decimal and divide by 3. So I'm going to come back here. I'm going to do natural log of the previous answer. So I want to push the second key, and then that a and s is on the negative sign. Get that, and divide by 3, because that would match my work, okay? So my constant is going to be about 0.01448, la, 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 all the things that were on my calculator screen. So my model is y. I'm going back now, my eyes are looking at this red, and I'm filling in the blanks. Y equals 6.08 e to the 0.0145, let's say, x. Okay, so that is my equation that I could use as a model. And then part B said find the population in the year 2015. Remember that we are measuring time starting in the year 2000. So this is as if I'm saying x equals 15. Okay, so all I have to do is plot 15 into the equation up here. So 6.08 e to my constant times 15. Now that constant is still on my calculator screen. So rather than round it unnecessarily, I'm going to use it. And I'm going to say, all right, I would be plugging in 15 up there in that exponent. I am going to take e to that answer, e to that result. And then I had 6.08 billion as my initial value. Okay, and so I got about 7.555 billion. When I looked that up on the interwebs, it kind of was an overestimate. So the growth rate between these 2 years maybe overshot what happened in reality. That's what modeling is. Modeling is our best estimate of what would happen before it actually happens. All right, let's take a look at this. A population of 800 beetles. You can decide if you want to think of the beetles as band members or as bugs, okay? Mr. Covey thinks they're band members. So a population of 800 beetles is growing exponentially. So after a month, this is an edit here, okay, to the question in case you printed early. After 1 month, there are 841 beetles. Okay, so that's what we're looking at. Write an equation that expresses the number of beetles at time x. Okay, so this is very similar to the question we just did. You have an initial value of 800. After a month, you have 841. We want to make use of this exponential growth model. Okay. So I want you to try this one yourself because it is very, very similar to the previous question. So I'd like you to do part A and I'd like you to do part B, and then we'll come back and do part C together, okay? Pause the video and see if you can do this on your own. Okay, check your answers. You can see in part A, we substituted in the things that we knew. We solved for k, so you would divide by 800 and then take natural log of that result. You should get about 0.05-ish, okay, depending on how you round it. And so your equation is there in black. In part B, you plug in 8 in place of the x, and then it's just a computation. I did round to a whole number there because we're talking about beetles, and I really don't want a fraction of a band member or a fraction of an insect, either one. Okay, and then in part C, it asked how long will it take for there to be 2,000 beetles according to our model. So we're going to make use of this equation in black. I want my population to end up as 2,000. I started with 800e. I'm going to round this on my paper to 0.05 times x. So the algebra here is first divide both sides by 800. That will give you 2.5 equals e to the 0.05, or however many decimal places you have, x. Then you're going to take the natural log of both sides. The natural log of e is 1. Okay? You also can just look at this as I'm just changing forms. I'm changing from exponential form to logarithmic form. Okay, so if you don't like that idea of taking the natural log of both sides, that's fine, right? The blue equation and the green equation mean the same exact thing because a log is an exponent, and that's what I wrote. And then if I just work this out, natural log of 2.5, divide by my decimal, I should get that x is about 18.326 months. Okay, 1.5 years of beetle growing population. Oy. Okay, so for the next part of our lesson, we're going to see a lot of problems that are very standard within a math class, but not very standard in real life. Now, that said, I still think they are valuable exercises to do. So this format that we were just looking at, one of the changes in variable that you sometimes see is calling this y capital A, calling this a capital P, etc. I mention this because you might recognize this already from your second year algebra class. So this is sometimes referenced as the PERT formula, and it is used in contexts where you're talking about the fictitious situation of having an account, like an investment, a bank account or something like that, where there's a continuous growth rate that is cited. Now, the rate that is cited in problems such as this is not the kind of growth rate that we were talking about before, where we had, you know, the A times B to the K times X kind of model, okay? So we sometimes would say, like, if it's a 2%, change, we'd have like 1.02. That is not the kind of growth rate we're talking about here. In these questions, they're trying to streamline things and just tell you what this constant up here, that I didn't highlight very accurately there, they're trying to just tell you what that little r is, okay, is what they're trying to do, okay, or this little constant right here is. They're trying to just tell you that. Now, as teachers, don't think that it's always very clear, like what is being referenced as a growth rate. So we will do our best to try to communicate that clearly to you, because we even find in looking at problems from other sources that it isn't always 100% crystal clear. And we want to be 100% crystal clear. Okay, so in these problems, we are looking at the very silly kind of thing that does not actually happen, but we think money is interesting. I could not resist. Okay, so even though this isn't necessarily the reality of how things work, we're still going to look at it, okay, just to practice the math of it. And so you can think of using this equation, like if that's something that you already know from another class, but understand that this is really just a special case of this situation, right? You see how, like, the things are all in the same slots, they're just labeled differently. That's not really a difference, okay? Not mathematically anyway, okay? So let's run through these. So this one says Dash invested $10,000 with Fantasy Bank at 3% interest compounded continuously. So this compounded continuously tells me that I'm using this kind of model. How much will he have after 8 years? So my setup is going to look like this. 3% is 0.03 as a decimal, and 8 years. So legit, those are all numbers. I just typed that in. So please find the answer to 1 and set up 2 and find its answer, and then come back to see me. Well, not see me. You know what I mean. Okay, so hopefully you can just enter that in your calculator, lickety-split, and you got the right answer for Dash. And then for Kimmy, you can see my setup and my answer. One thing of note is that I did round to cents, because that's how money usually works in our currency, okay? So even though our typical rounding rule is 3 decimal places, here I would say 2 is more appropriate, just because of the context, okay? Similar to like talking about the beetle question. Maybe you want to round to a whole number sometimes, okay? If you're ever unsure, you can ask, or just go 3 decimal places and we will not get mad at you, okay? Okay. All right, so number 3 is Cindy. Cindy invests some money at 2%. If after 6 years she has that amount, what was her initial investment? So initial investment means like what you start with. So whatever letter you have here is what you are solving for. So on your calculator, all you have to do is find out what this part equals, and then take the $16.91 and 25 cents and divide by that to isolate the A, or the capital P, or whatever letter you want to use there. And that should come out to being almost exactamundo $1,500. Okay. Question 4, I definitely want to walk through, because this is solving for a different like position in our equation. So here it says we want Jen to accumulate money up to this value. Okay, so that's what she has eventually. She starts out with $2,150, and she has this 2% that's given, and we are wondering how many years. So we're solving for, I'm going to use a T because I do think that helps my brain remember that that's time. So in solving this, I'm going to divide by 2150. So I'll just show my work a little bit here. Okay, and when I divided by 2150 on my calculator, I got that this side was 1.27125, la, la, la. And this side is e to the 0.02 times t. This is what I'm solving for. So since what I'm solving for is up in the air, I need this to be log form. So personally, I just think of taking natural log of both sides. You might think of it in terms of I just am switching form. Right, so put it in log form one way or the other. If you take the log of both sides, use down and front as the property that you're using there. Natural log of e is 1. And then you're going to divide both sides by 0.02. And you should check on your calculator that you did this right, you should end up with about 12 years, almost exactly on the nose. Okay? So for the last couple questions, these are ones that are similar to problems that we've already done. It does say in number 6, it looks different because you're solving for the interest rate, and you might say, but we haven't done that. It's just like this question, except instead of solving for this, you're solving for that. Okay, so the algebra is not really drastically different. So what I'd like you to do is to pause the video, do 5 and 6, and then come back, and then we'll take it from there. Okay, so I was just challenging myself for something that I could say here about these questions, but I don't know that I really have more to say. Number 5 is just a division question once you set it up. Number 6, going from purple to green, is a division step. Going from green to black, I'm taking the natural log of both sides. In your work, you might have gone from green directly to blue if you just thought about putting it in log form. Going from blue to the other line of green writing is dividing by 5. And then from the green to my circled answer is just rewriting a decimal as a percent. Okay? All right, let's look at these questions. Now, as silly as it is to think about having banks that do compound interest the way that we just described, it is much more plausible to think about something that has applications in biology. Okay, so let's take a look here at bacteria. Oh, how fun. Okay, so a certain type of bacteria, given ideal conditions to grow, right, like some petri dish with the exact right temperature, that type of bacteria doubles in population every 6.5 hours. So given that there are approximately 100 bacteria to start with, how many bacteria will there be in a day and a half? Now this has a little secret hidden, well, not secret, not hidden at all, but it has a tricky spot here in that one amount of time was given in hours, and then we were asked about in a day and a half. My understanding of a day and a half would be that that is 36 hours. Okay, 24 hours in a day, and then half as much again, okay? So what we're looking for here is we're saying, okay, if there was 100 bacteria to start with, that's this point. And, oh, sorry. Oh, no, that's what I meant. Sorry, having a moment. And then at 6.5 hours, we have double that. Well, that means I have 200. Okay, so that's the situation that we're looking at. We would be able to start working on our equation by saying, okay, I have 200 if I start with 100. And that 200 comes about after 6.5 hours. So I'm solving for this constant that describes then kind of the rate at which I'm growing, okay? So I'd like you to finish this question as best you can, okay? You should be able to do that with your skill set at this point. Okay, so we are dividing by 100, going from green to orange. We are switching the orange equation into logarithmic form in the blue equation. And then we are dividing both sides by 6.5 to get our constant. And then now that we know our constant, we can go back to the original equation, not have the 200 in there, but still have the 100 because that still was our initial condition. So 100 e to our constant, 0.10666, whatever, times 36, because a day and a half was 36 hours, and we should come out with 4,648 bacteria, rounded to a whole number because of whole number bacteria, okay? All right, our last question deals with actually a situation of loss. So we can have exponential growth, but we can also have exponential decay, and we can still be using this kind of model. Okay, it works for exponential growth and it works for exponential decay. So it says here the value of a mortgage brokerage company has sadly decreased from 7.5 million in 2010 down to 6 million just 2 years later. So this is telling me two ordered pairs. If I think of 2010, right, if I kind of look ahead, it does hint that number of years after 2010. So if this is time equals 0, this would be time equals 2. So I have the ordered pairs 0, comma 7.5, and 2, comma 6. Those are my two ordered pairs. So if I work on finding my equation, it would look like this. 6 is one of the ordered pairs if I put in my x coordinate as 2 at the same time. This is my initial value. Okay, and so these two values are just there because that's one of the ordered pairs. This is here because it's my initial condition. Okay, and as I'd work this out, I would divide by 7.5. I would put this into log form, and then I would divide by 2. And so your constant should come out to be negative 0.11157 and some more digits, okay? Now, something that I would point out here is that the k value being negative is what is going to tell us that this is a decay situation, okay? So right off the bat, right, anytime I have decay, this should come out to be negative. All right, now let's go back to our equation. Take out the things that are only sometimes true, keep the things that are always true. It's always true I started with 7.5. I just found that this constant is about negative point, let's say 112. And I have some amount of time. Now, obviously, if I have more digits for this constant on my calculator screen, I'm going to certainly make use of them. Part B says find when, so we're solving for t, find when the value of the company will be $4 million. So if I substitute in a 4, my algebraic steps are going to be to divide 4 by 7.5, that's 0.53 repeating, is going to equal the rest of this without the 7.5 on it. I would switch to log form, and then I would divide by that negative 0.112. So my time value came out to be 5.634. But remember, that's the number of years since 2010. So bear that in mind in answering the question. I do think that is all we have for examples. Hopefully that was enough examples for you to know what to do with the problems. So thank you very much, and don't hesitate to reach out to your teacher if this lesson was confusing to you in any way. Thanks.